So what if your camera could actually follow you? I'm not talking about some digital zoom trick. I mean, physically turn its head to keep you perfectly in the shot. It kind of sounds like something out of a sci-fi movie, right? Well, the tech is totally here, and we're about to break down exactly how it works, piece by piece. You know that feeling when you're on a video call and you accidentally wander off screen? Or maybe you're a creator trying to film yourself without a whole camera crew? It's frustrating. Well, this technology is the answer. It's like having your own personal automated camera operator. So here's how we're going to tackle this. First, we'll cover the big idea behind it all. Then we'll give our system a digital eye so we can actually see. After that, we need a digital brain to figure out where you're looking. Then we'll connect it to some muscles to make it move. And finally, we'll see what this thing can actually do in the real world. All right, first things first. Let's start with the big idea. Before we dive into all the code and hardware, what are we really trying to do here? What's the main goal of a face-following camera? When you boil it all down, the concept is beautifully simple. It's just a conversation happening between software and hardware. The software sees your head move and it tells the camera, hey, follow that person. You move left, the camera pans left. You look up, it tilts up. It's like a digital puppet master pulling the strings in real time. Okay, that sounds simple enough, but how does a computer actually see a face in a chaotic stream of pixels? I mean, that's the first huge challenge, and it all starts by giving our system a digital eye. Think of it as a two-step dance. First, you've got a regular old webcam acting as the eye. It's just constantly feeding video frames into the system. But then, this is where the magic happens. Super smart software jumps in and scans every single one of those frames, looking for a face. And not just a face, but the specific points that make it a face. Now, to handle that constant flood of video, the system uses a library called OpenCV. You can think of it as the essential bridge that connects the physical webcam to the software's brain. It's the tool that basically opens the door and lets the software see all the raw data pouring in. But just seeing the data isn't enough, right? The system has to understand what it's looking at. And that's where a tool called MediaPipe from Google comes in. This thing does the real heavy lifting. It's been trained to not just find a face, but to pinpoint dozens of specific landmarks on it, like the corners of your eyes, the tip of your nose, your chin, all of it. So by mapping all those little points in real time, MediaPipe basically creates a live digital skeleton of your face. This mesh of landmarks is constantly updating, and it's the absolutely crucial data the system needs to figure out exactly how your head is positioned and where it's moving. Okay, so the system has its digital skeleton. It can see a face. Great. But a bunch of dots on a screen isn't a direction, right? How does it translate all that data into a simple command like move left or tilt up? Well, this is the job for the digital brain. This is the really clever part. The software takes the coordinates of that digital skeleton and runs some quick math to figure out your head's orientation. It's basically asking itself, okay, based on where the nose is compared to the eyes, how much is this head turned to the side and how much is it tilted up or down? But hang on, there's a tricky little problem here. If you lean closer to the camera, the distance between your eyes and pixels gets bigger. If you lean back, it gets smaller. That could really throw the system off. So the solution is something called normalization. Instead of looking at raw pixel distances, it calculates the ratio of distances between your facial features. That way, it understands your head's position perfectly, no matter how close or far away you are. Now, you know how raw data can be? It's messy, it's noisy and twitchy. If the system just reacted to every tiny little twitch of your head, the camera movement would look super jittery and robotic. So to fix that, the data gets passed through a smoothing filter. This technique basically averages out all the tiny jitters, and it transforms that frantic, raw data into smooth, fluid, natural movement. So we have vision and we have calculation. The computer knows exactly where it needs to point the camera. But how does that digital command actually escape the computer and make something happen in the physical world? This is that final crucial bridge. The information follows a really clear chain of command. The computer figures out the final smoothed out angles, then it sends that data through a simple connection to a tiny microcontroller. And that microcontroller then turns around and tells the motors exactly what to do. And that little microcontroller, that's an Arduino. You can pretty much think of it as the system's central nervous system.
It can't see or think on its own, but it is brilliant at taking simple commands from the brain, the computer, and turning them into electrical signals to control the actual hardware.
So what's the Arduino actually controlling? Well, you can think of them as the muscles of the system, two little servo motors. One of them handles the side-to-side, or pan movement, and the other one handles the up and down, or tilt movement. And together, they give the camera its full range of motion. Vision, brain, nervous system, and muscles. All the pieces are connected. So, what happens when we put it all together and actually bring this thing to life? The result is exactly what we set out to build. It's a seamless, responsive camera that can intelligently track a person's head movements in real time, with absolutely no human operator needed. So why does any of this matter? I mean, what's the big deal? Well, the potential uses for this are just incredible. Think about it. Automated cameras for streamers, robots that can actually make eye contact with you, smarter surveillance systems, or even assistive devices that let people with limited mobility control things with just their gaze. Look, if there's one big thing to take away from all of this, it's this. When we combine computer vision, smart calculations, and some simple robotics, we can start to build machines that are just more aware of us. We can create tech that doesn't just wait for you to click a button, but that actually interacts with us in a much more natural, human way. And honestly, we're just scratching the surface here. Now that you get the basic building blocks, from the digital eye all the way to the robotic muscles, it really just leads to one final big question. What amazing thing would you build with it?